Let's unpack this. Today, we're diving into MiniMax-M1. It's a new open-weight, large-scale reasoning model. And it seems like it's really pushing the boundaries, especially, with complex tasks and handling really long inputs.
That's right. Yeah, this isn't just another model popping up in the leaderboards. MiniMax-M1 introduces some genuinely significant, almost academically interesting innovations, both in its core architecture and, importantly, how it was trained. They're tackling some pretty fundamental limitations we've seen.
Gotcha. And for our material today, we've got a good stack of notes and excerpts here. Still the most important insights from all this. Help you understand the core innovations of MiniMax-M1 and kind of see where it fits in this, rapidly evolving landscape of large reasoning models, like a shortcut to the cutting edge.
Absolutely. So let's maybe start by setting the stage. What's the big problem they're trying to solve here, and what's their sort of fundamental approach?
Okay, right. So we've seen large reasoning models, LRMs, getting much better at complex thinking, often using techniques like large-scale reinforcement learning, RL. Models like OpenAI's O1 and DeepSeek-R1 really showed the power there.
But there's always a but, isn't there? There's this fundamental technical hurdle when you try to extend that reasoning length continuously. Where does let's say, the old guard run into trouble?
Yeah, where's the bottleneck?
Precisely. So the dominant architecture for years, as you know, has been the transformer. And its Achilles heel, especially for long sequences, is that traditional softmax attention. It has quadratic computational complexity relative to the sequence length.
Quadratic. Okay, so just to make that concrete.
Yeah, imagine if every time you doubled the length of a document you were processing, the actual computational effort, like the number of calculations, quadrupled. It just becomes computationally prohibitive really fast for truly long contexts. Now, people have explored mitigations, right? Before 2024, things like sparse attention, linear attention, state-space models, even linear RNNs. But many weren't, let's say, fully validated at the massive scale needed for these top-tier LRMs.
Okay, so MiniMax-M1 steps into that specific challenge. It's a direct attempt to break through that quadratic barrier.
Exactly. That seems to be the explicit goal from the MiniMax team. Build the first open-weight, large-scale model specifically engineered to efficiently scale computation during inference, especially for those long, complex reasoning processes that just need more runway, more context, or longer outputs.
Efficiency is the name of the game then. So how do they actually achieve this fundamentally different scaling? What's the magic sauce?
Well, the core approach, according to the sources, is this hybrid architecture. It combines a mixture of experts, MOE structure, with a completely novel mechanism they're calling lightning attention.
Okay, let's unpack that. Hybrid MO. MOE isn't totally new, but mixing it with lightning attention, that sounds like the core innovation. How does that work?
Right, so the hybrid architecture is in MOE, but it's clever about what it mixes. It includes traditional transformer blocks, the ones that still use the standard softmax attention. But it intersperses them with what they call transnormer blocks, and these use the new lightning attention. The notes mention a pattern, like a 1 transformer block for every 7 transformer blocks.
Okay, specific ratio.
Yeah, and this MOE design is crucial right off the bat for efficiency, because out of a massive 456 billion total parameters in the model, only a sparse subset, about 45.9 billion, actually get activated for any given token being processed.
Ah, so you're not lighting up the whole massive model for every single step.
Exactly, which immediately improves efficiency. But the real architectural leap you mentioned is that lightning attention.
Right. Tell us about that.
Absolutely. This is where they fundamentally change the scaling. The sources describe it as an IO-aware implementation of a linear attention variant. They reference some prior academic work there. But the key takeaway is, unlike the traditional softmax attention we just talked about, the one that explodes quadratically, lightning attention achieves near linear scaling with sequence length.
Near linear. Okay, that sounds significant. For processing or generating massive texts, what's the practical impact of near linear versus quadratic?
Think of it like this. Near linear scaling means the computational cost, let's measure it in FLOPs, floating point operations, basically a count of calculations. It increases much, much more slowly as the sequence gets longer. It doesn't explode. This dramatically cuts down the processing power needed during inference when the model is, thinking and generating text. And crucially, it also helps during that large-scale reinforcement learning phase needed to teach it complex reasoning. Less compute per step.
And the sources actually put some numbers on this efficiency gain, right? Compared to other models.
They do, yeah. pretty compelling ones.
Yeah.
Compared to DeepSeek-R1, for example, at a generation length of 100,000 tokens, which is pretty long, MiniMax-M1 apparently consumes only about 25% of the FLOPs.
Wow, a quarter of the computational cost at that scale?
Yeah, it's a huge gain. And partly because of this architecture, M1 natively supports a context length of up to 1 million tokens.
1 million tokens? That's massive.
It is. The sources point out that's 8 times what DeepSeek-R1 handled, and really an order of magnitude more than other leading open-weight LRMs around its release. And this capacity, this ability to handle huge contexts, is a direct result of that lightning attention. It's essential for tasks like, summarizing enormous documents or engaging in really long multi-step reasoning chains.
Okay, so the architecture gives it the horsepower for these long sequences. But teaching a model to reason deeply often involves that reinforcement learning step you mentioned. And the sources talk about a new RL algorithm, CISPO. What specific problem does that solve in this whole picture?
Right. This is another really core technical innovation they present. So previous large-scale RL algorithms like PPO or GRPO, they often use this technique called token clearing. It's kind of like putting guardrails on the learning process, preventing huge destabilizing updates during training.
Okay, sounds sensible. Keep things stable.
It does, but it had a significant, perhaps overlooked drawback. This clipping could inadvertently stop contributions from crucial, often low-probability tokens.
Low probability tokens. Why would low probability tokens be crucial? What kind are we talking about?
That's the interesting part. The researchers found that tokens associated with what you might call reflective reasoning behaviors, words or phrases like however, or aha, or wait, let me recheck that. Maybe let's consider this alternative. These are often assigned low probabilities by the base language model.
Because they're less common than just describing things.
Exactly. They're less common than standard descriptive text. But these tokens are vital pivot points in a reasoning process. They represent the model, like pausing, considering, maybe changing direction, essential for complex thought chains. So when RL tries to reinforce these valuable behaviors, the gradient updates for these low probability tokens can be really large. And traditional clipping would just snip them off, ignore them, which hinders learning sophisticated reasoning. Even DPO, which tried to increase the clipping bound, apparently wasn't fully effective in the M1 setup.
Okay, so CISPO comes in. It's specifically designed to make sure these critical thinking tokens do contribute to the learning process.
Precisely. CISPO stands for Clipped IS Weight Policy Optimization. That's MiniMax's proposed solution. Instead of clipping the magnitude of the token updates themselves, which PPO GRPO did, CISPO clips the important sampling weights.
Okay, that's a technical distinction. Why does clipping the weights instead make a difference?
It's key. By clipping the weights, which are used to account for the difference between the distribution the model is currently sampling from and the target distribution it's learning towards. By clipping those, CISPO ensures that all tokens, even those with high update values that would have been clipped before, still get to participate in the gradient computations. Their information isn't lost.
Ah, I see. So it makes the training more stable and more effective at capturing those subtle but important reasoning steps.
Exactly that. It stabilizes the training, reduces variance, and significantly boosts the overall efficiency of the RL process. The sources even cite a controlled study they did using a different model, Qwen3-235B. But in the similar setup, which showed CISPO achieved a 2x speedup compared to DPO.
A 2-time speedup, that's substantial.
It really is.
Yeah.
And this algorithmic breakthrough, combined with the efficient hybrid architecture, was apparently fundamental to getting M1 trained. The sources note the full RL training for M1 was completed in just 3 weeks on 512 H800 GPUs for an estimated cost of around $500,000, 0.53 MUSD.
Wow. For a model of this scale, 3 weeks and $500,000. That sounds incredibly efficient.
It's impressively low, yeah, and directly enabled by these technical and algorithmic advances working together.
Now, training these huge models, especially with novel architectures and RL at this scale, it's never straightforward, right? The sources mention some specific, maybe non-obvious challenges MiniMax hit during RL training because of this unique hybrid setup. What were some of those stumbling blocks, and how did they get past them?
Yes, that's a great point. Scaling RL to a novel hybrid architecture like M1 definitely threw up some unique, kind of low-level technical hurdles they had to figure out. The sources detail a few critical ones.
Okay.
First, they ran into something they called a computational precision mismatch. Basically, they found that the probabilities the model assigned to tokens during the training process weren't matching up well with the probabilities in the actual inference mode, the mode where the model would eventually be used.
Huh. Why would those be different?
Well, the sources show a figure illustrating this discrepancy, and it was directly stopping the training rewards from consistently improving. They noted it wasn't really an issue in smaller, standard dense models, suggesting it was linked to this new architecture. Their analysis pinpointed unexpectedly high magnitude activations happening specifically in the final output layer, the LM head.
Okay, so the very last step was behaving unexpectedly.
Right. And the solution wasn't trivial. They had to meticulously analyze this and then increase the computational precision of just that final LM output head layer to FP32, a higher precision format. This seemingly small technical fix boosted the correlation between training and inference probabilities from like 0.9-ish up to about 0.99, which was crucial for getting stable reward signals and making the training actually work.
Wow, a precision tweak in one layer fixing the whole reward signal? Okay, what else?
Second, they faced significant optimizer hyperparameter sensitivity. The Atom W optimizer, which is pretty standard for deep learning, turned out to be unusually sensitive to its specific settings, the beta values, the epsilon values specifically with M1's gradients. They found the gradients during M1 training had this really wide range and also weak correlation between different training iterations. This combo caused the optimizer to just not converge with the standard default settings.
So the usual settings just didn't work.
Apparently not. The solution needed detailed analysis of these gradient properties, followed by careful, specific tuning of Atom W. They landed on specific values: beta 1 0.9, beta 2 0.95, and epsilon 1 E15, much smaller epsilon than usual.
Okay, fine-tuning the optimizer itself. And there's a third one.
Yes, interesting one. Early truncation via repetition detection. During training, especially if you gave it a complex prompt, the model could sometimes fall into this pathological state. It would start generating extremely long, repetitive, often nonsensical responses, just looping.
Right, models sometimes do that.
Yeah, but these runaway outputs generated huge gradients that would destabilize the entire training process. And just trying to match repeating strings wasn't reliable enough to catch all the ways it could get stuck. So the solution they came up with was actually quite clever, a heuristic based on token probabilities instead of a rule. Holt generation, if 3,000 consecutive tokens, each had a probability above 0.99.
Because the probability spikes when it gets stuck in a loop.
Exactly. They observed that probabilities go way up when it enters one of these repetitive modes. So this method effectively caught and stopped these pathological outputs, preventing instability and also improving the training throughput because they weren't wasting compute on generating useless loops.
Those sound like really deep system-level problems, the kind that could totally derail a project if you didn't find those specific fixes. Overcoming those must have been absolutely critical for making large-scale RL viable with this new architecture.
They definitely were. Finding and implementing those specific solutions seems fundamental to achieving stable, efficient training at scale with this hybrid lightning attention design. It really highlights the intense engineering effort required to push these models forward.
Okay, so moving on to how they trained this beast. The sources really emphasize a focus on reasoning-intensive data and using diverse environments during that critical RL phase. Can you walk us through that training pipeline?
Sure. It was definitely a multi-stage strategic process. They started with their existing MiniMax-Text-01 model as a base. First stage was continual pre-training. They added a huge amount of data, 7.5 trillion additional tokens, but the key was the focus of that data. They made it very reasoning intensive.
What does that mean, reasoning-intensive data?
Well, they state that 70% of this new data came from high-quality sources in STEM fields, code repositories, books, and also curated reasoning data sets. And they really stressed data quality here. Meticulous parsing, better cleaning to remove noise, prioritizing natural data over synthetic stuff where they could, and semantic deduplication to avoid just repeating the same ideas. Oh, and for the long context part, they used a smoother, staged extension of the context window, starting at 32K tokens and gradually increasing it up to the full 1 million.
Instead of just jumping straight to 1 million.
Right. They found this gradual increase helped prevent gradient explosion issues, which was apparently particularly important for the earlier layers in that lightning attention mechanism.
Interesting. Okay, so after more pre-training.
After pre-training, they did supervised fine-tuning, or SFT.
Yeah.
This was described as a cold start, SFT, meaning done fresh after the pre-training. Its main goal was to specifically instill desired behaviors. The key focus here was injecting reflection-based chain of thought, COT, reasoning patterns. They used a data set of high-quality examples for this, and a big chunk, 60% of this SFT data, was detailed math and coding problems and solutions. providing a really strong foundation for the next, more complex RL stage.
Got it. So pre-train for breadth and reasoning focus, SFT for specific code behaviors, and then the core RL.
Exactly. Then came the core reinforcement learning stage, and this is where they use that strategically diverse set of problems and environments to really hone the model's reasoning abilities. They kind of group these environments into two types. First, rule-based verification tasks. These are problems where you can deterministically check if the answer is right or wrong. So mathematical reasoning problems, logical reasoning tasks they mentioned using a synthetic generator called SynLogic for some of these competitive programming challenges, and software engineering tasks. For software engineering, they actually built specialized sandbox environments based on the SWE benchmark. This let them get execution-based rewards. The code the model wrote actually had to compile and run correctly to get a positive reward.
So direct feedback on whether the code works.
Precisely. Rewards that were mostly about correctness and maybe following the right output format. The second category was model-based feedbacks. This was for more open-ended or general tasks where simple rule checking isn't possible. Things like general instruction following, creative writing, summarization perhaps. For these, they used generative reward models, GenRMs. These are basically other models trained specifically to evaluate the quality of the main model's responses. Often using a pairwise comparison setup, the GenRM looks at two responses and says which one it prefers.
Right, using another AI to judge the first AI. But the sources mentioned a potential issue there, length bias, that these reward models sometimes just prefer longer answers, even if they aren't actually better. How do they deal with that?
Yeah, that's a known tricky challenge with RL from human feedback or model feedback. The reward model can learn a superficial proxy for quality, like length, and the main policy can then exploit that, becoming overly verbose without getting smarter. MiniMax tackled this systematically. They implemented continuous online monitoring of this length bias during the actual RL process. If their monitoring metrics showed the policy was starting to just generate longer stuff to game the reward model, they would trigger a recalibration of the GenRM. And on the RL training side itself, they also used techniques like reward shaping, value clipping, and normalization specifically to make the training less sensitive to just superficial length and more focused on the actual quality of the reasoning and the solution.
Okay, so active monitoring and adjustments on both the reward model and the training process. Makes sense. And all this careful multi-stage training, this diverse RL setup, this is what allowed them to scale the actual thinking length during training itself.
Yes, that seems to be the payoff.
Yeah.
They explicitly extended the maximum generation length the model was trained to produce during RL. They went from a limit of 40,000 tokens, which resulted in the model variant called MiniMax-M1 40K,
Yeah.
all the way up to 80,000 tokens for the MiniMax-M1 80K model.
Doubling the trained thinking length.
Right. And this scaling also used that stage window expansion idea again, gradually increasing the length limit during training. 40K, then maybe 48K, 56K, and so on, up to 80K. This gradual process was apparently guided by how the 40K model was performing. It also involves some data filtering, like removing easier samples, focusing on harder ones, and downsampling certain synthetic data types that they found could cause instability at longer contexts. And they mentioned having to implement specific fixes again to handle instability that popped up due to the length differences between examples during this longer context. RL scaling, using things like that repetition detection, early stopping, combined normalization strategies, and adjusted clipping parameters.
So a lot of careful tuning and problem solving even during the scaling phase of RL. Okay, so after all these innovations, the architecture, the CISPO algorithm, the careful training and data strategies, how does MiniMax-M1 actually perform? What do the benchmarks say?
Yeah, the payoff. The sources provide quite a bit of evaluation data across a range of benchmarks. Table 2 and Figure 1 in their paper summarize a lot of it. And the results are pretty compelling. They really highlight M1's strengths.
So how does it stack up generally?
Overall, it clearly establishes itself as a very strong contender among open-weight models, performing comparably to or sometimes exceeding other really powerful models like DeepSeek-R1 and Qwen3-235B. But where it really shines, where it seems to pull ahead, is in those complex tasks that demand deep reasoning and handling large amounts of information. Specifically, the benchmarks show particular strength in complex software engineering. They mentioned SWE bench-verified tasks, which involve fixing real bugs in real code bases.
Okay, practical coding ability.
Right. Also, an agentic tool utilization measured on TAU bench, which tests how well the model can use external tools to solve problems, and especially in long context understanding benchmarks like OpenAI MRCR and LongBench v2.
And how does it compare to the big closed models in those areas?
Well, this is where it gets quite interesting. In these specific challenging areas, M1 often surpasses some of the leading closed-source models. The sources explicitly show it outperforming OpenAI's O3 model and Claude 4 Opus on some long context understanding tasks. And it apparently beats Google's Gemini 2.5 Pro on that TAU bench for agentic tool use.
Wow, okay. That is significant. Outperforming top commercial models, even if just in specific demanding areas.
And did they show that scaling the thinking length going from 40K to 80K actually helped?
They did, yeah. That's a key finding they highlight. The MiniMax-M1 80K model consistently outperforms the M1 40K version across most of the benchmarks. So it's not just about having the capacity for longer thinking. It demonstrates that actually enabling the model to produce those more extensive reasoning processes leads to better results on the tasks themselves.
And there was one figure, I think figure 4 in the sources, that seemed to visually connect accuracy gains with longer responses during RL training. What's the significance of that specific plot?
Yeah, that figure is really a crucial piece of evidence, I think. It provides pretty strong empirical validation for the whole core idea behind M1's design. It shows that enabling the model to generate longer, more detailed reasoning outputs, essentially giving it a bigger internal computational scratchpad or thinking budget, which the efficient architecture allows. That ability directly correlates with, and seems to cause, improved performance on tasks that genuinely require multi-step thinking, like math problems, or coding challenges, live code bench, shown in the plot. It confirms that efficiently scaling the test time compute isn't just some technical achievement, it's a functional pathway to getting better reasoning capabilities.
Okay, so wrapping this all up then, MiniMax-M1 really stands out because of this unique combination of technical pieces coming together.
Exactly. It's the hybrid architecture with that lightning attention, fundamentally changing the scaling to near linear for massive contexts. It's the novel RL algorithm, CISPO, allowing stable and efficient training by making sure all the important gradient information gets used. And it's those targeted specific engineering solutions that overcame the unique hurdles of training this kind of model at scale. All built on that foundation of extensive pre-training on reasoning-focused data and diverse RL environments.
And these deep technical innovations are what let it really push into areas where older architectures maybe hit a wall, handling huge amounts of context, solving complex problems, needing long chains of thought, even acting like an agent using tools.
That seems to be the case.
Yeah.
And importantly, they've made the MiniMax-M1 models publicly available on GitHub, Hugging Face alongside offering commercial API support. So the work is out there for the community to use and build on.
Right. The sources definitely frame this as more than just, one more model release. It feels like they see it as laying a strong technical foundation for what's next, especially for LRMs acting as more capable agents tackling complex real-world challenges, things like automating workflows or maybe even assisting in scientific discovery down the line.
That certainly seems to be the aspiration. And it leads to a really provocative thought to leave listeners with, perhaps. If enabling longer, more extensive, more computationally affordable thinking is a key bottleneck we've been facing for solving certain classes of really hard problems, what kind of previously impossible challenges might these efficient architectures, like the one in MiniMax-M1, finally allow future AI agents to start cracking open?
That is a powerful question. What becomes possible when thinking gets cheaper and longer? A great place to end our deep dive today. We hope this breakdown helps you feel well-informed about the key innovations and the significance of MiniMax-M1. Definitely keep exploring the details yourself.